Thank you, Sarah. Good morning, guys. I'm happy that so many of you found their way here after last night's party. I am Heiko, and I'm actually with a company called Pebble. We are mostly known, yay, rocket. We are mostly known for smartwatches. So I saw a few there. Who of you knows what Pebble is and Pebble does? That's basically everybody. Who does not? Well, there are a few. Okay, I have a few slides for you too. So the thing you're looking at is basically the PCB or the main board of our Pebbles. This is a disassembled version of this Pebble here. And when I speak about wearables, I want to share the learnings we gathered when we made JavaScript running directly on our limited hardware. And I want to walk you through some of those limitations and then again what we learned from doing so. So again, for those 3 or 4 people who don't know Pebble, it is basically a smartwatch. I like to think of us as the first mover, those who first came out with a smartwatch long before Android Wear or Apple Watch. And in fact, our watches work with both iOS and Android, and unofficially also thanks to our community on other platforms. We do obviously notifications, but recently we emphasize on health too, where our latest model has a built-in heart rate monitor. We do step tracking, sleep tracking, smart alarms that wake you up when you're in REM phase, and so on and so forth. We are best known for our long battery life, lasts for a week instead of a few hours, and it's an always-on display, which is quite neat. But the reason why I'm here is because it's hackable. You can actually program on it, and we emphasized on a very open API and open app approach from day one. And that led to a plethora of different apps. So there are hobbyists such as like sailors or surfers who benefit from Pebble being waterproof, but there are also big brands such as Uber or Nest who give easy access right on your wrist to their services. So with Uber, for example, it's really just a button press away and that taxi comes and picks you up. And there's also another category, obviously, on a watch, and that is watch faces. There are tens of thousands watch faces by now, developed by our community. And they are animated, they are colorful, they are very delightful, and it's great to see that. People always say that our platform is a bit limited, but it just happened 2 weeks ago that a demo classic, a PC demo classic, was ported to Pebble and presented at one of those demo parties in Germany. And that kicked off a conversation in our community, and there's now a Slack channel discussing how we could leverage that and create a demo scene just within Pebble. That's all great and amazing, but traditionally on embedded devices, and Pebble is no exception there, you are forced to write code in C or C++, and sometimes, when you look at that demo, even in assembly. And that is mostly because of that hardware being so limited, space-wise and also performance-wise. Which is a bummer because C sometimes looks like this. And that is great C, actually. I looked it up on a blog post, and he walks us through this piece of code that does what exactly? Who can tell me what it does? String concatenation. Yeah, that's true. I mean, the function name obviously states that, right? It takes basically an array of strings and concatenates it into a buffer. C has no concept of a string. And you have to allocate the buffer before and tell it how long the buffer is. The counterpart in JavaScript would look like that, maybe. Like you have an array of strings and you join them together. I'm pretty sure there are other ways to do it, but this is pretty neat, isn't it? Now, what stops us from doing that? There are plenty of other devices that do JavaScript on there, and they are all embedded. I did a quick research to find some of those, and this is the list I came up with. I'm pretty sure I missed some, and my apologies for this, but I just want to put things in perspective here. And to do that, I picked some arbitrary metric here, the amount of available RAM of those different devices. And if you look at Intel Edison or the Raspberry Pi, they have 1 gigabyte of RAM, which is basically not a limited embedded device anymore. That's a real computer. And then there's the Omega 2, there is the Tessel, and they are more within the range. It's 64 megabytes, and if you think about it, booting a Linux, for example, in that environment is already a bit tricky, but certainly doable. And then there are others, Esperino, like by Gordon Williams, for example. He kickstarted this great embedded device that does nothing but runs JavaScript. And how much RAM do they have? Why? Don't they have any? Well, the problem is scale here, and I try another attempt. Here, gigabyte is far too large, and I'm scaling that down to 64 megabytes, and if I zoom in and zoom further, I finally find Espruino Pico with 96K and Pebble offering only 64 kilobytes of RAM to applications. 64 kilobytes compared to those 64 megabytes, that's a fraction of 1,024 of that other amount. Like, that's tiny. And I understand that this is hard to understand, so I will try once more. This is the JSConf Iceland website, and you see that little icon at the top left. That's an SVG. That file is 25K large. SVG is known to be very concise. In this particular case, because it is actually a bit curved, maybe it is not optimal for an SVG, but it's pretty small. The pixel data on my laptop on this particular screenshot, though, takes already up more space than the 64K available on Pebble for applications, just to put things in perspective. So it's not only the code, it's not only JavaScript, but actual data, and all of that needs to live on that computer. Things are not that bad, though, because people already build great things. We know that you can accomplish something, so, well, let's do it. So there are plenty of JavaScript engines, right? We take one of those. Again, yesterday ran a quick test, and I loaded google.com on my Chrome browser, and it took 155 megabytes. Or I looked at the engine itself, which is yet another number. Even if we had a JavaScript engine, it somewhat would take up code space on our Flash, on our firmware. And before we started this endeavor, we figured that we would have 200K worth of code space, Flash code space, something you would normally not even think about when you do web development. And Phantom.js, which is basically a headless browser based on JavaScript core, already takes up 32 megabytes. So this is way out of reach. And when we presented internally at Pebble the idea to run an interpreter and even JavaScript on our Pebble watches, they thought we were crazy. This is not possible, it will not run at all, and we still said, we want that. We want that so deeply because the workflow in C is outdated. It takes 20 seconds for a turnaround. When you do pixel nudge some things, you need to compile, you need to deploy, and then you look at it, and you already forgot how the previous version looked like. I want to have fast tooling as it's common in the JavaScript world. I want to have the ability to benefit from you, the community, all these NPM packages, all the knowledge that's there. I want to go to Stack Overflow and quickly copy and paste something and run it on that watch. Well, luckily, there are other JavaScript engines out there meant for embedded devices. I think the most prominent one is called Ducktape. Ducktape is taking a few 100K of code space. You could probably squeeze it down. Then there's obviously Espruino. JerryScript, a very interesting project. Kinoma looks also very promising. And then there is, similar to any other JavaScript library out there, every week pops up another JavaScript engine, basically. So here are a few. The problem with those tiny, I would say, hobby attempts is that they are oftentimes not standard compliant or by far feature complete. So in the end, we decided to go with JerryScript. And when Gordon Williams from Espruino actually asked me, I came up with that list here. And it's basically, first and foremost, JerryScript. All of them are open source, obviously, but this one here has a great team behind it, full-time people working on this for over a year now, which is amazing. Because we have to stand on the shoulders of giants here. We cannot do that all ourselves. But it's also standard compliant, so whatever you do in valid JavaScript will actually run on the watch. And that is critical because otherwise it's yet another script language that is a JavaScript lookalike, but not the real thing. And overall, it's just the quality of the project. Communication, architecture, all of it, plus partners that contribute to it, as we do. So that's great. And I think it took us, so we first did an Espruino port, and that ran on the watch. And then we did JerryScript again, and it was early May when we finally shipped JavaScript on the watch. So those people in the audience who actually were a Pebble, if you go to the standard watch face, TikTok, the one with the two hands, that is already running JavaScript without you knowing it. We shipped the JavaScript engine. We re-implemented our standard watch face. We have integration tests to make sure that it's pixel perfectly the same and it doesn't consume more battery as the C counterpart did. And we shipped it. Now that was easy. The hard part and the stuff I want to talk about is our learnings when we finally made that available to developers, which is also happening right now, actually. And the three things I want to focus on are APIs, memory constraints, sorry, bear with me, but memory is really critical in our platform. And then launch time, something that isn't really obvious if you think of it, about it for the first time. So APIs. I was talking about JavaScript. Well, JavaScript by itself doesn't do much. Again, here's our board. There's the CPU and the MCU, which combines different components, in our case, the CPU and RAM. And JavaScript, what can you actually do with it? I mean, in the standard, there's state, there are regular expressions, there are different things in the standard. But you cannot even log anything because console log is not part of the standard. So just having JavaScript by itself is actually a bit useless. We want to give access to everything our platform delivers, and that is way more. So here is a teardown of the actual watch. This is not two different boards. At the bottom, you see the flip side of the same board, so it's mirrored. And the MCU is really just, that's JavaScript, that's granted. But there is also flash storage. That is where we store the program and store your bitmaps and other resources like custom fonts. There is obviously the e-paper display. You want to show something on the screen, and battery, so that if you happen to be a taxi service, you could check the battery level, and if it's critical, you could raise the fare. Like, there are real use cases for access to the battery. And then there is also all the sensors and the Bluetooth radio. You want to talk to your phone, you want to talk to the internet. How would we possibly make that accessible? The problem with APIs on our end is, unlike a library, an API developer who does the next library and publishes it on NPM, is that we cannot really do semantic versioning, raise the major version number, and break everything that was ever there, because developers are using our SDK, submit this to the App Store, and consumers run whatever version of the firmware. There is actually the problem that once we commit to an API, we more or less have to support it forever. And that is really a delicate problem as an API designer, because we don't have the luxury to break APIs here. We are much more in the shoes of a browser vendor here. And that's actually the key to the story. There are standardized APIs for all of these problems, and you know them, they're called web APIs. So although we are running on this tiny embedded hardware, we chose to look at the browsers and learn from them, and basically re-implemented what they did. So for the display, for example, we chose Canvas, and it's ugly as hell, and it's really inconvenient to use, but it's a standard. And that means others know already how to use it. They know the pitfalls, and there are already solutions to the problems that come with it. There's a contract we can commit to, and we know that it will not change. Well, at least not that frequently. And similarly, for communication between the phone and the watch, our gateway to the internet, we chose a post message, as you would talk to another window or a background worker, and use an event system for different occurrences in the system. So that is all great, and it led, together with NPM, to a very concise way to writing applications. So this is a very minimal way of writing apps. You can actually use NPM packages, and with that, we hope that people write polyfills and create other convenience functions, but this is also the way to get access to the root object of our API. We called it Rocky, as in like stones and Pebble, you know. And that Rocky global allows you to register, to listen to events, such as when it has to draw itself. The system could ask for it to draw at any time because of different events in the system. And the web APIs being so flexible allow us to also add new proprietary events, such as minute change. When you write a watch face, for example, it's not really feasible to redraw every second, because that drains the battery. If you really only want to update once a minute, it's also hard to do the date math with just the built-in date object. You could totally do that. You could query for the current time and then do a set timeout and then schedule a redraw. but we actually provided convenience events for this, like minute change, second change, so that you know on the edge when the minute changes that you can redraw. So that's it, pretty neat. But with those standard APIs, we also created some expectations. So Canvas is pretty powerful, and some of its implementations, for example, clipping to a path, is difficult to implement on our platform. A naive and very performant and efficient solution would be to store a binary mask, or actually like an alpha channel, to measure what is actually masked out. But such an alpha channel is already on our platform, like 6K worth of data, and we are really short on RAM. And then other things, as I mentioned before, on Canvas are not really convenient, especially if you come from our C API, where we tailored it towards the need of a watch face developer. Yes, angles are rotated clockwise, but they start at 3 p.m., which is very inconvenient if you want to do hands and they all start at 12 o'clock. And then also drawing a simple line means, yeah, you begin a path, you move to something, you line to something, and then you stroke instead of just a plain line call. So yeah, that is odd, but it's just the standard. What we figured is that, and we talked to the community, that we cannot ship all of this at once. What we did instead is we ship what we have. We know what the target is because it's just the web APIs, and just like fail with exceptions when a function is undefined. That allows developers to create polyfills, and it's actually better to have something now than to wait another half a year or something until we finally did this. So I'm also interested in your feedback on this. So yeah, with that, we basically shipped APIs. Let's talk about memory constraints. So there are, like when you talk about size in JavaScript, you oftentimes think about transfer, like how many bytes do I need to transfer from the web server to my browser in order to deliver content? How can I get the first byte to the browser earliest? How can I leverage caches? But this is actually pretty meaningless. So this one is a demo. I'm not sure you've ever seen this, but there's a competition very much like the demo scene in general. It's basically how much cool effects can you squeeze into 1K worth of JavaScript. So let me quit that again. I'm not sure why it's stuttering here, actually. So yeah, that is 1K of JavaScript. The JavaScript looks like that. It's concise, yeah, it's only 1K. For those of you who cannot read gibberish, what's actually happening here is that there is a compressed string. The actual payload is almost 2K worth of JavaScript source code, and then this is the loop at the end. We uncompress it into a variable, and then we eval it. So basically, instead of running 1K of JavaScript, we are running almost 2K of JavaScript. So one could think that we just expanded it 100%, and at runtime we need 2K worth of RAM, right? Well, I took the numbers again on Chrome, and it's more like half a gigabyte roughly. And of course, this is like comparing apples with oranges here, because the browser itself takes up RAM, and the GPU process, like the rendering pipeline here, has a lot of overhead for this particular use case, and you could make that way more concise. But this is really just to put things in perspective. Code size 1K has nothing to do with runtime requirements, how much RAM you actually have. And I would say that you guys have no idea about RAM. Or could you tell me how much RAM this object actually takes? Like JavaScript has no concept of an out-of-memory situation. You can always just create a string. You can always just create an object. But what if you run out of RAM? Well, this does not happen in your environment. So here, for example, you need actually character space to store the property name. You need space to store the original string. You need more space to store the concatenated string, to store O, which is living on the context. How much is a string worth? Is it really stored as UTF-16? Do you know what CESU8 is? Their way to encode emojis because they don't fit into the Unicode plane of Unicode 16? Like, how much cache do they actually do in order to look up the property? Do they have like a hash map for the string lookup? Probably. We do. So it's really tough to tell. Let's say, like, conservatively on V8, maybe that is, I don't know, 32 byte? Probably not, maybe 64 byte. If you store 10 of those, it's already 640 bytes. That's like in the range of something you can notice on our platform. So we wrote a couple of tools to analyze bytecode, to analyze heap consumptions, but we quickly realized that this is not the level a typical JavaScript developer want to operate on. So what we did instead is we introduced an event. Oftentimes it's basically going like this. I program until this is not enough RAM anymore, and then it crashes. Well, that's great, but I could actually prepare for this scenario. If you are, like memory leaks are one thing, but oftentimes you have structures that could be recreated if you have had more RAM later on. So what we do is we actually fire an event when you have high memory pressure, and then you could let loose of resources you don't need anymore. And there's another occasion when this event fires, and that is really the critical piece, when if you don't let loose now, we actually quit your application. Well, interesting question is, how would you possibly do any logic here if you're out of RAM anyway? So let's talk about performance then. Luckily, JerryScript, unlike other embedded runtimes such as Esperino actually parses the same source code again and again. If you jump into a function, it parses that function again. If you jump out and jump into it, it parses it again. JerryScript is way more efficient. It stores a code in bytecode, and that is great, but computing bytecode up front costs time and RAM, and you guys know it by now, we don't have that RAM. So what we did come up with is a system where we produced bytecode offline. You have your own program stored in a folder structure. Our SDK bundles JavaScript for the phone and JavaScript for the watch, and it also compresses some of the resources. And then if you install an application, we actually move the JavaScript part to the phone. That was already true for the last 2 years. And now the crazy thing happens, which we call JavaScript inception internally. We basically cross-compile the JerryScript compiler using Emscripten to JavaScript so that we can take your JavaScript and produce JavaScript bytecode in JavaScript. And that is for different reasons. One of them is that the bytecode is no real ABI contract. It actually depends on the firmware. But on iOS, for example, you cannot download any new executable code unless it's JavaScript. So, and there are different other reasons, and I'd love to talk about it. But in the end, we actually only store the bytecode on the watch, executed in the JavaScript environment. Point 4 is what we were talking about here. And then you have access to the API, talk to the internet and everything. That is crazy. But we did it. We shipped that like 1.5 weeks or 2. We finally made that available to developers, and this is how it looks like. So in the shell, you have this SDK thing. You can build it. And then we already at build time tell you where you have problems, not at runtime, but actually at build time. And we can do that because we leverage TypeScript under the hood. You are not aware of this, but we actually have like TypeScript definitions for all our APIs, which are basically web APIs, and know that a property is not available or like you have some tactical errors. And then you build it, and you can actually deploy it. On the right-hand side, you see an emulator, which this is not a simulator. It's really it maps the memory and everything one-to-one as it exists on our physical devices. And there you can run a watch face. It's not the most obvious watch face here, but it's done by one of our community members, which is great. We also have the ability, because we have a local SDK, to tie this with your favorite IDE. Here I'm using WebStorm. That is also done by one of our community members. This is as you look at the structure of the code, he's actually inspired by C. He comes with a C background, which is fine. It actually tells me that JavaScript is approachable enough for a C developer, whereas the other is not obviously the case. But here, I'm showing that we actually have code completion thanks to TypeScript definitions. So we know what we are dealing with. We can store that. We have, at type time, we know if something is incompatible and so forth. And that is also great. And because all our projects are now like real, they do have a package JSON, they can require other things, we can now leverage all the tooling. So I can now run scripts that are defined in the package JSON to build my program, which is basically the same I did previously in the command line, and also to install it, which will then again fire up the emulator. So that's all great, and that's basically the same thing, but I really only put this here to show you that this is for real, and you can download it now and use it and do JavaScript. So here, for example, that's a re-implementation of Apple Watch's Hermes watch face. And there's a third thing, and we have this for a while now. It's called Cloud Pebble. It's a cloud-based IDE, traditionally for Pebble native applications where we offer you a code editor. It was previously in C, now in JavaScript. And it's, again, the same code. It's the same author. You actually see that some of the sections are the same, and I hope that the community will create NPM packages from this to deal with repetitive tasks in watch face design. The crazy thing about Cloud Pebble is what it actually does, because it's not, the editor is running in the browser, but we have a cloud-based build system. So whenever you actually do something, it's transmitted to the cloud build. And then the emulator you see is also hosted on the cloud and streamed via VNC back into the browser where you can see the picture-perfect result. But it allows you to basically write JavaScript-based applications anywhere where you have access to a browser to run it either in the emulator or directly on the watch. And it depends on the remaining time to actually show that on the actual watch. So yeah, that is there. And here you see that we deal with different like screen shapes and different aspect ratios when it comes to our platform, which is all doable. That's now, let's talk about the future. Because this is not the end. This is not what we want to do. What we really want to do is we want to do great debugging. So here's right now we only have console log, for example. But what you see here is built with everything that's publicly available. On the left-hand side, you see a node server, which does not really do much. It's basically taking keyboard input, relays it via WebSocket to our phone, and then whenever it receives something from the phone, it prints it out on the shell. So I'm running that node server. And on the right-hand side, there's our Pebble application. It consists of two parts. One is the part that runs on the watch, physically on the watch. It's trivial. It's basically whenever a message comes from the phone, eval that string, take the output, and send it back. So that's the watch part. And the same project also has the phone part. And the phone part is also just a relay. It talks via WebSocket to the node server. Whenever it receives a string from the node server, it forwards it to the watch. And whenever it receives something from the watch, again, just message passing here, it forwards it to the WebSocket connection, which is the node server. And with that, and just the building blocks you should all be familiar with, we created on our platform a REPL. So I start this application now. Again, by now you should be familiar with it. It's an emulator, but now we are also printing the logs. Here's the emulator. And as soon as I launch this, both parts will be connected to each other, and boom, there we are. So we can eval simple expressions, 2 + 2, well, that's not really surprising. But if I log something, that log output doesn't appear on the left-hand side on my node server, but it's actually logged in the context of the watch. And because this is really a rocky application, I can also do everything we saw previously in the source code. So I'm now registering an event handler that whenever it fires, it prints hello JSConf Iceland. Obviously, that doesn't fire immediately because nothing told it to redraw, but I'm requesting now a redraw, and boom, here we are. So this is really a node server talking over the phone and Bluetooth to the watch, printing something and interacting with it. So we started a bit late. Sarah, can you tell me how much time do I have left?
You have plenty of time. You have like...
Awesome.
Yeah.
That's enough for me. So for the next thing, I actually want to do it for real and a live demo them. Because like you saw that installing these applications takes some time. Because we still do the same tool chain. We technically still build a Pebble application. And under the hood, there's still a tiny little piece of C that does nothing but telling the system, okay, yeah, cool, I'm standard compliant, I'm a C application, but you know what? I don't want to do anything but eval that bytecode that's also part of my package, which was magically done by this mind-blowing Emscripten thing before. But what if we could shortcut that even further? So we did now the other way around. So what you see here is yet another watch face. It's actually, that is more or less the source code of our built-in watch face. And I can run this in the browser. So let me open that here. That is running in the browser, although there's no Pebble involved. And you could say, well, that's not a problem because the APIs are Canvas, aren't they? I can just draw to Canvas and get the result. Well, the problem with an environment like this is that you want to have pixel-perfect results as you are developing. because the resolution is so small and you really want to see all the quirks and all the bugs we introduce in our platform. So what this is actually, yes, the original source code, but it lives within an HTML page, which uses a transpiled version of our firmware inside the browser. So again, we are leveraging Emscripten here, but this time we cross-compiled the firmware, actually the application layer of our firmware, to run inside of the browser so that we can talk to it in the browser. And that gives me fast feedback because I'm now in my IDE and I can say, you know what, that black is a bit depressing, let's make that yellow. And if I make this and reload that page, boom, it's yellow. And I can change that white to red, reload it, and there we go. And then this white is really hard to see, and I make this black. Cool, so that's where we are heading. This is what we want to gain, right? This is the development we want to have, but eventually we want to run it on the watch, so let's do that. I'm copy and pasting that into the IDE we saw before. I'm pasting it here, and then you can choose between different targets. I'm now taking, again, the emulator, and while I'm doing that, to see that it actually works, taking off the watch I have here on my wrist, and put it on the video setup I have here on the right. So this is a live camera. This is actually you here in the back. And I can put my watch here so that you can see the actual output. And by then we started the emulator, have it all installed here, and well, live demos. Let's see, do maybe make this black again. Sometimes the IDE doesn't, if I just paste, maybe it didn't understand that I was changing code and didn't recompile really. So I'm now expecting red hands and a black background. There we are. Okay, cool. So I'm changing that a bit more. I'm saying CTX fill style is yellow. And then I'm saying CTX fill text, hello, JSConf Iceland at 10:10. And I'm changing that to not talk to an emulator, but actually to the phone. And that is, again, crazy. What it does now is it understands that my phone using my Pebble account is connected to the cloud. It pushes the binary, it compiles it in the cloud, then it pushes it to the phone, it talks via Bluetooth to the watch, deploys it there, and what you see on the right-hand side is still the old application, but I think you got it, it's now running on the watch. So this is really the real thing. You can write JavaScript, modify it, and deploy it on a watch. Cool. So with that, I come back to my slides. This was my backup. What you just saw is JavaScript running on the watch. It's really like the real thing. It's your JavaScript, your Canvas code, your events, and everything right there. If you are a Pebble developer or want to be a Pebble developer and C scared you in the past, go there, try it out, give us feedback. It's available. If you do something with embedded devices, and you have a hard time thinking that this is possible, we have plenty of internal knowledge and learnings, and I would love to talk to you. If you just got here by accident and actually wanted to watch the other presentation in the other room, the message to you is you bet on the right horse. JavaScript is everywhere. It reaches even down to those little devices, and you can be sure that JavaScript will be around for a long time, and there will be more and more devices for you to play with. Thanks.